this year's new final exam. Right, so you will you will get familiar lah with uh, the apa tu pattern ataupun how the final exam will look like lah. Sebab ikutkan you will be sitting for face to face final exam nanti, right? So nanti saya akan bagi that two questions at the end of the class through Google Classroom. Okay, so for to those who haven't joined in our Google Classroom, please do so because nanti you will be submitting the answers through Google Classroom as well lah, right? So saya harap you will take the advantage of this Tuesday cuti tu untuk siapkan soalan yang dua ni lah. So more or less we have up to next Wednesday, okay, to finish up the two questions, okay. Similar question, it's just that dia walaupun dia dua soalan tapi dia punya figure tu sama. It's just that the approach the question tu berbeza. Okay. Nanti you boleh tengok nanti bila saya share at the end of the class. Right. So saya share screen ni. So nanti attendance link saya akan bagi di hujung kelas juga. Right. Right. So we will recap what we have learned earlier during the first class of this chapter 2. Kita recap sedikit So you have gone through chapter 2, the statics of particle. Okay, so in the first class, you have been introduced to a resultant of two vectors. So what will happen if we add this vector P to NQ, and it will add up to become a resultant force lah. Right, so dia punya syarat asas is sekejap, ada yang record kan? Sebab I cannot record sebab saya tak. Ada yang record?
Belum lagi tu.
Okay, so boleh record lah. Okay.
Sekejap Bagi saya 2 minit.
Okay, tak apa. Along the way ni you boleh record lah. Sebab dia pun ada limitation of time kan? Right, so tak apa sebab saya pun nak recap dulu. So this is if we add up this P plus Q, it will become a resultant force of R. So remember that if these two forces coming out from a similar point A ni, ini kita panggil dia concurrent forces. Alright, so concurrent forces apabila lebih daripada satu vector, okay, coming up from this similar point. Right, so dia punya hasil tambah, so resultant force dia would become R. So syarat dia adalah when you add up two force, vector force, Tak boleh draw. Okay. Okay. Yep.
Doktor, saya dah start record.
Okay, sure. Alright. So let's say we have these two vectors. Alright. Saya recap sebab takut ada yang datang. Last week. Last. So kita ada dua vektor. This is P. This is Q. Okay. So if we look back on the parallelogram law, which said if two vectors represented by two adjacent sides of a parallelogram, okay, dia adalah selari satu sama lain. Okay. So this is also P. This is Q. So meaning these two vectors are parallel to one another. So dia punya resultant force would be the diagonal of the parallelogram, right? This is, let's say this is the R, right? So sebabkan dia adalah walaupun pada mulanya the gambar rajah menunjukkan dua vektor ini di sini, okay, concurrent force ni di sini, but because it is a parallelogram, okay, parallel to one another, right? So we can get the resultant force to be the diagonal of the parallelogram. So ini adalah hasil resultant of this P plus Q, right? So this and then we have also touched on equal vectors. So equal vectors meaning it has the same magnitude and direction, right? Negative vector is if the equal vector is in opposite direction. So this is P, this is negative P, right? This is negative vector, ni adalah equal vector. Alright, so vector addition juga adalah bersifat commutative. Alright, it doesn't matter if you go this way, okay, P plus Q ataupun Q plus P, it will still give us the same resultant vector force vector, right? And then vector subtraction pula it is when the The second vector is in inverse, is in reverse direction lah from the first one. Right. So you have to know that the resultant force, okay, the direction of the resultant force must be from the tail of the first force ni to the head, to the head of the second ataupun last vector. Okay, because vector addition can be more than two vectors added together, right? So in this chapter also we have touched on law of sines and also law of cosines. So this law of cosines and sines can also be applied, okay, in order to find the vector addition. Okay, kita tengok kita punya info yang kita ada lah, info yang diberikan menulis gambar aja ataupun menulis soalan. So you jot down all the important information and then you see lah if you can use this uh, law of cosine and law of sines ni to um, solve the question, right? So this is when the vector addition is more than it involve more than two vectors. So sekali lagi, the resultant force must be the direction of resultant force must be drawn from the uh, tail of the first vector. So this is P, right? First vector, okay, to the head of the last ataupun third vector lah. So this is S lah, right? And it is also known that addition of vectors dia bersifat associative. So associative kat sini, it doesn't matter this parenthesis P plus Q ataupun Q plus S, but the resultant force atau resultant vector ni masih akan menunjukkan direction yang sama. So contohnya kat sini, vector P plus parenthesis Q plus S, okay, it still end up here, okay, because this Q plus X comes from these two addition of these two vectors, okay, Q plus S. So drawn from the tip, right, ataupun tail from Q to the head of S, right? So it doesn't matter. And then we have also multiplication of a vector by a scalar. So bila kita cakap pasal multiplication of vector by a scalar ni, hanya scalar yang bertambah lah, okay, ataupun berubah. So this is 1p, this is 1.5p. This is the next one is in reverse direction, so negative 2p, but the amount of but the scalar is now 2 times than the original p. So negative 2p. Okay. And then we have the current forces. So apabila a set of forces which pass through the same point lah, right, it coming out from the same point. Alright, so again dia punya vector addition pun sama lah. Okay, dia menggunakan pakai a parallelogram. For two vectors can use parallelogram ataupun triangle rule. So basically kita ada 4 method tu: parallelogram law, kita ada triangle rule, kita ada polygon rule for more than 2 vectors, addition of more than 2 vectors, ataupun kita ada rectangle rule. So rectangle rule ni adalah di mana we will resolve that force vector, okay, that single force vector into its components, force component. So ingat satu force vector can have 2 or 3 force components lah. So force component ni dia akan dalam sebutan X, Y, Z, dalam sebutan unit vector ataupun sebutan koordinat X, Y, Z lah. So kita tengok, right. So we have gone through this one. Right, so this is the fourth method, rectangular components of a force by resolving this single force into its force components lah. So the force component on Cartesian coordinate would be resolved into fx and fy. Kalau the 3-dimensional, it would involve 3D. That is rectangular component in space. Nanti kita akan baca kejap lagi apabila dia akan involve exact axis lah. So it will become fx, fy, and fz. Okay. This single force, this single vector force, this single force vector is resolved into its component. So component f, component x, and component y. Right. Okay. So ini adalah method yang keempat lah. Okay. So if we have a force vector ni, the resolve dia into its fx and fy. So it will become a rectangular vector components. Right. And then it is also said that we have a unit vectors ij, okay, which represent the direction of fx and fy. Alright, so dalam unit vector ni, dia punya magnitude adalah bersamaan dengan 1. Okay, the direction is diwakili dengan sebutan I and also sebutan J untuk Y axis, I untuk X axis. Kalau untuk Z axis later on kita akan ada sebutan K. Right, so vector components may be expressed as products of the unit vectors with the scalar magnitudes of the vector components. So yeah, from here, alright, we can express this force vector in its unit vector form. Alright, so F, vector F is equal to Fx. This is the magnitude, okay, magnitude of this force component in X direction, right, times dengan I, vector I. Vector I menunjukkan dia punya direction is on X axis. Right, so ini scalar ya, Fx ni scalar. So you tengok different dia. So ini adalah vector. Ini ada sebutan vector component. Kalau dalam sebutan unit vector component, so it will become scalar times dengan dia punya unit vector I. So this is the scalar, the nilai vector tu dekat X axis. Ini menunjukkan direction of that vector is in X direction. Okay, and so it goes for the Fyj as well. Right, so Fx and Fy are referred to as the scalar components of F. Right, so ingat kalau you express that rectangular vector, that force vector in its rectangular in its unit vector form, okay, so that I and J is representing the direction, Fx and Fy adalah dia punya scalar. Right, okay. So nanti you boleh tengok balik lah. So we have gone through this earlier, this in the last class. So nanti tengok sebab kita nak masuk equilibrium of a particle. Alright. So what is meant by equilibrium of a particle? So it is said that when the resultant of all forces acting on a particle is zero, the particle is said to be in equilibrium lah. So basically in statics ni kita akan hanya jumpa keadaan di mana particle ataupun rigid body tu dalam keadaan equilibrium. So summation of forces dia akan will be equal to zero. Okay, so itu in engineering statics lah. Okay, sebab so for something to be in static ataupun dalam keadaan not moving, so dia mesti in equilibrium lah. So apa-apa daya yang bertindak ke arah sesuatu objek ataupun partikel itu mestilah dia memberi summation is equal to zero. So that is why that particle is static. So ingatlah kalau untuk engineering statics ni kita hanya akan fokus on equilibrium. Okay. So Newton's first law said that if the resultant force on the particle is zero, the particle will remain at rest or will continue at constant speed in a straight line. So the particle will remain at rest lah, right? Tidak bergerak lah. Sebab tu in statics kita hanya perlu cari nilai force tu. Okay, nilai force factor yang menyebabkan that particle ataupun body static. Okay, ataupun at rest. Right. So if you have a particle acting at this point, acting on this point A, okay. So acting on this point A, if you have a particle A, right? So if there are two forces acting on this particle A, okay. So for this particle A to be static ataupun remain at rest, so that two forces must be equal in magnitude but in opposite sense and also same line of action lah, right? Baru dia akan jadi equilibrium. Right, so kat sini as I told you in the last class, so a line of action is the line to the point at which the force is applied lah. Okay, so kalau kita ada di sini, right, so if you have this, okay, P, right, so ini adalah line of action. Okay, so this P can be translate, okay, along this line of action. Alright, as long as it is moving along the same line of action, dia adalah dia tidak berubah apa-apalah. Okay, so yang ni kita akan tengok masa chapter 3 nanti. Right, so ini adalah line of action lah. So kalau kita ada kat sini satu lagi force, that is force vector Q. So this is line of action untuk Q. Okay. So ini untuk Q punya, yang ni untuk P punya. Okay. So if we have more than two forces ataupun kita panggil concurrent forces, okay, on this particular point A ni, alright. So how to solve for these forces ni? If it is said that this that the particle A is in equilibrium, so kita boleh pakai graphical solution which yield a closed polygon ataupun kita pakai algebraic solution, right? So this is where resultant, iaitu the resultant of these four forces, okay, ataupun summation of these four forces is equal to 0, right? And then as we resolve this force vector into its component f dalam sebutan vector force in x direction, vector f in y direction, so kita akan samakan dengan 0 lah untuk mencari dia punya nilai resultant tu, right? So ada soalan tak setakat ni?
Belum je tu.
Okay. So as you I believe during kalau kamu datang daripada matrix ataupun dari matrix lah, saya rasa mostly saya ambil statistik ni daripada matrix kan. So I believe you korang telah pun tahu tentang free body diagrams lah. So bila kita ada something, a system ataupun any phenomenon, kita boleh represent that phenomenon ataupun sistem tu dalam dia punya FBD, free body diagram. So you have to know how to draw free body diagram lah basically, right? So kat sini kita ada, so we have a lorry here, alright. So kat sini kita ada dua orang pekerja, alright, tengah menarik puli ni, okay. and then at the same time there's a weight on the lorry. Okay. Alright. So a sketch showing the physical condition of the problem. This is the space diagram. So we have to represent this space diagram ataupun gambar rajah ni kepada demi free body diagram lah. So basically kat sini kita tahu ada weight. It involve weight of the let's say this is box lah, weight of the box. Alright, kita ada tension kat sini, kat AC ni, because of this man in yellow shirt is pulling this rope. Okay. The same goes dekat AB because this man is also pulling the rope. Okay, so it will cause tension lah dekat AB and also AC. So basically ini adalah dia punya free body diagram. So you have to know lah how to represent this action yang tengah berlaku di gambar rajah ini ke 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 free body diagram, right? So we tengok sample problem 2.4. Alright, there's a ship. Alright, there's a crane here carrying up a car. Alright, so at the same time there's a man. Alright, is trying to balance out this the weight of the car by he's pulling the uh, rope. Okay, uh, dekat particle A dekat point A ni. Okay, so dengan bersudut 30 darjah lah. Okay, meanwhile for this rope AB ni pula, okay, from the center from this point B, okay, at the tip of this crane dia akan melibatkan sedikit ada slanting sikit sebanyak 2 darjah lah. Okay. So in a ship unloading operation, a 3,500 Newton automobile, so berat kereta adalah 3,500 Newton, is supported by a cable. Okay, a rope is tied to the cable. And pulled to center the automobile over its intended position. So inilah lelaki ni tengah menarik ni to center the automobile over its intended position. What is the tension in the rope? Right? So kita cari what is the tension in the rope. So basically if you dapat soalan, please take out ataupun take note on the important information lah yang diberi, seperti berat kereta, okay, 3,500 Newton. So the F is equal to 3,500 Newton lah. F equal to mg lah, right? And then draw the free body diagram. Right, so construct a free body diagram for the particle at the junction of the rope and cable. Apply the condition for equilibrium by creating a closed polygon from the forces applied to the particle. Apply trigonometric relation to determine the unknown forces magnitude. Okay. So kita tengok dia ni. Alright, so basically, so insyaAllah kalau next week kita buat kelas online pun saya punya tab dah nak baik, so dah sedang sikit lah boleh draw ni macam susah sikit. Okay. Saya tak boleh nak draw, so I can only show you ataupun saya draw dekat dokumen lah, right? Sorry. So construct a free body diagram for the particle at A. Right, so this is the point ataupun the center lah of this kejadian, right? So A, so kita ada berat kereta iaitu F is equal to 3,500 Newton. Asas Wah. Alright, sorry Okay, I have to answer that question apa tu instantaneously. So sorry. Dengar kan? Dengar tak?
Dengar. Dengar.
Okay.
Dengar tu.
Alright, so construct a free body diagram for the particle at A. So A ni is like center of the gravity lah untuk this apa tu this is scenario, right? So and then kita tahu kat sini we have a weight of not weight lah, this is force, right? So ingat ni because dia diberi dalam 3,500 Newton, so this is force, right? F is equal ataupun tension lah, 3,500 Newton. Alright, jangan tersilap pula. Right. And then we have a tension due to this man is pulling in order for to make the kereta tu stabil lah. Okay, TAC with a degree of 30 degree, okay, downward from this center of ataupun center of axis ataupun center of gravity ni lah, right? So and then we have the crane, alright, the crane pulling. No, the crane is actually uh, uh, apa tu? Pulling with tension TAB lah, right? So ada sudut 2 darjah kat sini, so dia akan jadi 2 degree di sini lah, alright, from this center of action ni, right, A kat sini. So as we solve for the unknown force magnitude ni, so kita tengok so kalau kita tengok kat sini there are 3 concurrent forces acting on point A. Alright, so we can represent this concurrent forces into its triangle rule punya triangle rule punya method lah. Alright, so kita tengok kat sini 3,500 Newton is heading downward. Downward. Alright, so kat sini ada TAB with a 2 degree uh, uh, 2 degree something from this line of action, right? Okay, and then here heading uh, downward as well, tapi to the east. So kita ada TAC. So kat sini we can uh, convert this into a triangle method punya rule lah. Right, so turun bawah. So ni TAC. Alright, so now the angle between this is 120 darjah. Right. Okay, so ini antara TAB dan this force 3,500 Newton would be 2 degree. Okay, sebab apa tahu? Sebab as I told you earlier, so this is 3,500 Newton ni, force ni. Okay, dia boleh translate along it line of action. So ini adalah line of action dia. Okay, the y axis. Okay, so as kita translate dia ke sini, so the the degree the angle between TAB and this 3,500 Newton would become 2 degree. Right? Sebab tu dia jadi 2 degree kat sini. Right? So boleh. So TAC ni pula as you can see here, the degree between this 3,500 Newton to TAC is 120 darjah. Right? So that is why it is here 120 darjah. So what is in this figure, you hanya perlu convert it to a triangle rule method. Right? Ada apa-apa tak soalan tak untuk yang tu?
So far tak ada, Doktor.
Line okay ke? So in order for you to change it to this triangle rule form ni, so you boleh gerakkan this individual forces along its line of action lah, until it form a triangle lah. Okay. So as we want to solve for the unknown force magnitude ni, so kat sini as we kita ada advantage of knowing all the angle, okay, in between these two force vectors. Right, so kat sini kita boleh pakai sign rule lah, okay, untuk mendapatkan TAB and TAC. So you have to know lah berapa maklumat yang you ada. Okay, lepas tu you jot down all the information ataupun all the value that you have, and then you try out using any available equation lah, okay, yang boleh fit in. Right, it doesn't necessarily you use rectangular force component punya method, okay, tapi melainkan soalan tu dia state kat situ gunakan rectangular force component. So you kena buat cara yang tu lah, you kena find the force component for each vector. Right, so that is soalan 2.4. So kita tengok 2.6. Right, so it is desired, okay, ni kita ada boat kat sini. Alright, this boat dia drag force lah, it is dragging this cable. Right, it is desired to determine the drag force at a given speed on a prototype sailboat U. Okay, A model is placed in a test channel and 3 cables are used to align its bow on the channel center line. Right. So, ni ada 3 kabel ni. Okay. For a given speed, the tension is 40 Newton in cable AB and 16 Newton in cable AE. Okay, so sini 40, so this is AE. Determine the drag force exerted on the fuel and the tension in cable AC. Okay, so sekarang ni dia dah bagi kita tension AB ni is equal to 60, AE is 40. Dia suruh kita cari tension kat kabel AC and juga the drag force, okay, of this boat lah, sailboat ni. Okay. So choosing the hull as the free body, draw a free body diagram. So kita kena represent this scenario into its free body diagram. Express the condition for equilibrium for the hull by writing that the sum of all forces must be 0. Okay, for this sailboat to be in static ataupun remain at rest, so the summation of these 3 all forces acting at this point A must be 0 lah. Okay, so resolve the vector equilibrium equation into 2 component equation. Solve for the 2 unknown cable tension. Right? Right, kita tengok kat sini. So this is the free body diagram of this scenario lah. So we that seperti tadi kita telah beri AB sama dengan macam terbalik je. AB sama dengan 6. AB is 40, betul-betul. AB is 40 and AE is 60. Right, AB is 40, AE is 60. Alright, so kita ada force TAC kat sini, attention TAC due to this cable and also the force, okay, of this sailboat. Alright, so this sailboat is force FD lah. Right, so this is the center of gravity. Okay, not gravity lah, center of action. Right, for origin. Okay, so choosing the hull as a free body, draw a free body diagram. So you have already done that. Alright, so kita nak cari pula berapakah nilai. Okay, sebab A dengan B ni kita boleh cari. Right, so tangent A is equal to 7m over 4m. Right, 7m over 4m. So we akan dapat sudut di antara TAB, okay, dan juga TAE ni kat sini. Right, so tangent B is equal to 1.5 meter. So sini semua telah diberi di dalam gambar the value. Okay, 1.5 meter. Alright, over dengan 4 meter. Okay, so inilah kat sini 1.5 over 4. Right, so express the condition for equilibrium for the hull for by writing that sum of all forces must be equal to 0. So this is where kita ada this 4 force vector, right? TAB, TAC, TAE and also FT. Okay, so the sum ataupun resultant of these 4 concurrent forces ni must be equal to 0. Okay, because it is said to be in equilibrium. Okay, so kalau yang kat sini we have no other choice than by using the rectangular form. Okay, rectangular component, vector component punya equation lah. Right, so we have to resolve each, okay, vector ni, force vector ni into its vector form whenever necessary lah. Right, so kat sini kalian tengok, so this T, this is TAB. Okay, so this is TAB. Right, as we resolve it, because that force vector in negative x direction, so negative 40 Newton times dengan sine 60.26 I. So I is showing the direction of this force vector lah. Okay, in its x component. Right. Meanwhile, for the unit vector J pula, okay, so dia adalah 40 Newton cos 60.26 J. Okay. Ada masalah tak kat situ macam nak resolve a force vector into its component? Okay ke?
Doktor,
Ah,
ni dia dah start pecah X komponen Y komponen ke?
mm-mm.
Okay.
Okay.
Thank you, Doktor.
Sebab, okay, so ini adalah dia punya condition apabila this free body diagram is said to be in equilibrium. Okay, so apa yang kita tahu tentang ni is only dia punya force and also sudut lah. Right, dia punya magnitude of this tension. Okay, and also dia punya of these two tension and also dia punya sudut lah, sudut di antara dua force vector tu. Alright, so kat sini we cannot apply uh, uh, law of cosine ke, okay, law of sine ke, sebab tak cukup maklumat. Right, so we have to use rectangular force component. Okay, so kita resolve this this TAB and also TAC lah. Okay, so you tengok macam ni kat sini macam mana dia resolve kan. So kat sini TAC ni belongs to quadrant number 1. So positive X and also positive Y. Right, so kat sini positive X and also positive Y. Right. So this is basically so this is basically representing ini okay, so buatkan dia is equal AC sorry lah sekejap T C X plus T A C Y. Okay. Okay, kalau you ingat lagi kita ada buat yang tadi, kita ada buat recap tu. So ini dia bersamaan dengan yang inilah. Okay, saya boldkan T ni because saya nak menunjukkan this adalah sejenis force vector lah. Okay, dia ada magnitude and also direction. Okay, so TAC is equal to component of this force vector, the force vector into its x component plus dengan this force vector in its y component. Okay. So tapi as we change it to unit vector, dia akan become macam ni lah. So I is showing the direction. Okay. I is actually representing the direction of x ni. J ni untuk y direction. And this is the magnitude. Alright. So the magnitude is TAC. And this is also TAC. So cos 20.560 is the direction of this J, of this force vector from y-axis. This also from x-axis. Right? Alright, faham tak kat sini?
Faham doktor?
Okay. So as we saw for this one, alright, so sekejap dia hang sekejap Internet lambat. Sebentar. Right, okay. So and then, so this is for tension AB, this is for tension AC. Yang ini sebenarnya untuk T lah. So TA, just now kita tengok dia is TAE. Alright, so TAE is equal to negative 60 Newton I. Alright, magnitude and also direction because it is located on y-axis. Alright, so y-axis, so direction dia adalah bersamaan dengan 0. Okay. Yang ni salah yang ni J Ni alam. Salah ni J. Alright, so it is located it is located on y-axis. So dia punya I, direction I is equal to 0. Tapi yang untuk J dia ada value of negative 60 Newton J. Ni J Saya tak tahu nota kamu I ke J, tapi ini sebenarnya J.
I juga.
I juga. So this is supposed to be J lah. Because as you can see here, it is located on y direction. So dekat y direction, y axis, so meaning the coordinate of x is equal to 0, so dia akan jadi kosong lah untuk x component. Right? So untuk FD, because it is located on y x axis, so dia akan jadi FD, okay, the magnitude times dengan I. This is direction lah untuk x axis ni. Right. So hasil tambah ke semua ni kita equate dia to 0. Right. So kita akan dapat hasil tambah ni. Right. So you tambah semua ni. Okay. TAB, TAC, T and FT. And then you arrange it according to dia punya unit vector. Okay. You kumpulkan dia ikut dia punya unit vector. So I. Okay, this is for sebutan, apa-apa sebutan dalam J, untuk direction J. You equatekan kepada 0. Right. Okay, so you akan dapat FD is equal to 19.66. TAC is equal to 42.9 Newton. Alright. So you tengok balik, kalau ada question, let me know. Tengok sekarang tau. Boleh tak?
Boleh Doktor.
Okay. Saya proceed So additional exercise ni, so you can go through on your own ataupun kalau ada masa nanti kita boleh buatlah 1-2 soalan. Right? Sebab saya nak go dekat rectangular component in space. Okay. So now we are speaking of rectangular component in 3D lah. Tadi in 2D. So it only involve X and Y direction ataupun I and J direction. Now in space there akan ada 3 sebutan. Right? In unit vector K as well. Right. So kita tengok vector F, force vector F ni. Alright. So ini adalah 3 paksi. 3D lah. In space lah. So X, Y, Z. So basically vector F ni, okay, dia terletak di antara X and Y plane. Okay. Tetapi di atas paksi kosong. Right? So you tengok kat sini. Okay, so the angle between this y-axis to this force vector F is theta y. Right? So the vector F is contained in the plane OBAC. Right? Dia contain kat sini. Nampak tak? I mean, you boleh nampak tak that where the vector F is actually contained. Sebab kadang-kadang ada student yang ada masalah nak bayangkan vector in space ni.
Doktor, boleh Doktor terangkan sekali lagi? Saya kurang faham.
Okay. So let's say kalau awak bayangkan awak ada kotak lah. Kotak. Okay, so ini adalah kotak awak. Okay, so this is okay lah, sekejap. Saya lukis lah. Okay, vector in space. So basically, so ini adalah Z, Y, and X. So you can imagine this Z, dia punya paksi tu is going towards you, ke arah kita. Okay, Y ke atas, X ke kanan, and Z tu ke arah kita. Okay, so this is the ni. So basically, the plane. Harap bersabar lah sebab tak ada dekat nak draw. Okay, so ini adalah plane yang dikatakan tu. Right. Tetapi okay. So sorry, silap. Merah. Saya draw a box lah supaya you can easily see this one. Okay. Wah. Betul. Okay. So let's say this is a cuboid lah. Okay, so that force vector is actually located here. They're heading to here. Okay. Okay, so kalau you tengok balik kat sini, Dia dekat sini. Okay. Dia ke arah sini. So it actually located on this plane. Warna lain hijau. Dia menyentuh this ataupun dia contain in this particular plane here, kat sini. Nampak tak?
Nampak madam, nampak.
Nampak.
Okay. So this is actually the actual location of this force vector F lah. Dia terkandung di atas plane yang ini. Okay. Okay. So this is Fy. Okay, because the force vector, as we resolve this force vector into y. Okay, and also here. H is actually representing hypotenuse lah. Okay, sebab dia kat sini. Okay. So this is Fy is F cos theta y. Untuk Fh, dia akan carry F sin theta y. Okay. So yang H ni dia punya sebutan ni tak fix lah ya. Bukan yang perlu awak tulis H. You can namakan this line X, Y, Z lah. K ke ikut awak lah. Okay. Alright. So and then kita resolve this F H into its rectangular components lah. Because this one, alright. So dia terletak di sini, di plane yang flat ni. Right here. So kita resolve it into its components. Okay, kita ada Fx is equal to Fh cos phi. This is phi. Okay. So kalau saya namakan this sudut is phi, so dia akan ambil cos phi lah. Okay, so as we know Fh is equal to F sin theta y. So kita masukkan kat sini. Right. So yang ini sebenarnya nak bagi you pemahaman je macam mana it is actually carried out. You tak perlu nak hafal pun yang ni. Cuma you kena faham macam mana it is derived. Right. So Fy is equal to Fh sin phi. Fh sin phi. Okay, this phi, so the sin. Okay. So F sin theta y sin phi. Okay, kita replace. Okay. Because it is said that Fh is equal to F sin theta y. Right. And then the same vector force ni, right, we can also resolve it into its individual components lah, x, y, and z. Right, so Fx is equal to F cos theta x, Fy is F cos theta y, and z is equal to F cos theta z. So this theta x is located between the force vector to its axis. Untuk y, from this force vector into y axis. Untuk yang ni, to its z axis. Right? So sama juga konsep dia. So you can replace it with in its vector form. Alright. So F cos theta x ni, right, masukkan dalam sebutan vector form. So yang sepunya ni adalah nilai magnitude untuk F. Right, sama. Tapi directionnya berbeza. Will be depending on the angle between the two, between the axis and the force vector component itself lah. Right. So ini cos theta xi, cos theta vector I plus cos theta y vector j plus cos theta z. vector K ni is equal to F lambda. So lambda ni adalah satu rumus yang fix Okay. So lambda is a unit vector along the line of action of F. Okay, and cos theta x, cos theta y, cos theta z are the direction cosines for F. So lambda ni adalah untuk direction cosine. So yang ni you akan sentuh masa dynamic yang ni yang masa static ni kita hanya nak introduce you saja. Okay, lambda is equal to this sebutan. Alright. So saya rasa up to here mesti ada yang macam confuse sikit. Boleh follow tak? So ini you hanya perlu tahu saja.
Boleh, madam.
Okay. So nanti kalau you tak faham, you boleh tengok balik nota ni. Okay, ni adalah derivation saja. Okay. So rectangular components in space, it can also be calculated ataupun be obtained by using location of points ataupun point location. Alright. Kalau kita tahu that exact location lah, coordinate dia. Alright. So direction of the force is defined by the location of 2 points. So the M dengan N ni, because this force vector is starting from point M to N. So ini adalah location asal x1, y1, z1. Ini N, x2, y2, z2. So ini adalah koordinat masa dalam yang kita belajar dalam matematik tu lah. Nak cari jarak dia ini bersamaan dengan x2 minus x1, y2 minus y1, z2 minus z1. So ini adalah how far that this particle has translate from point M to N. Right? So this is the displacement lah. Okay, displacement sama dengan vector joining M and N. How far did that displace? Right? So it would become dx I plus dy j plus dz k. So this is the scalar lah. Okay. Ini yang menunjukkan direction. So this is how we write displacement. Okay. Of a vector. Okay. In between 2 points. Okay, dalam unit vector form lah. So dx ni scalar ni sama lah macam saya cakap tadi, x2 minus x1, dy y2 minus y1, dz is z2 minus z1. It's just that you have to insert this value in its direction unit vector ni. Okay, which carry out the direction punya representative lah. Okay, so force vector F is equal to F times dengan lambda. Right, so lambda just now is actually a unit vector along the line of action of F theta or F theta pula, of vector F. Right, so lambda is here. Okay. Lambda is here. So lambda tu sebenarnya dia terletak di atas F ni lah, vector force F ni. Okay. Sebab that lambda is actually representing resultant, not resultant lah, the single vector F tu punya direction. Okay, dekat sini unit vector lambda tu sama dengan 1. Okay. So kalau you tengok kat sini, this is where the lambda is located. Right. So lambda vector, so force vector F is equal to F, the scalar, value of the scalar, times dengan the direction. So lambda ni sama juga macam unit vector, tapi dia maksud saya dia sama dengan unit vector, dia menggambarkan direction of that single vector force tu. Okay. So lambda is equal to 1 over d. So d is the distance, right? Times dengan dxi plus dyj plus dz vector k. So ini adalah dia punya. So ini adalah direction dia. K ni IJK. This is scalar. Right. So D. So D ni adalah bersamaan dengan apa tu? Jarak. Okay, punca kuasa of x2 minus x1 plus y2 minus y1 plus z2 minus z1. Right, so D is here. Okay, so fx bila kita pecahkan dia balik kepada sebutan yang ni, jadi f dx. Right, so sebab ni lambda kan, so this is lambda. So you masukkan kat sini lambda ni akan jadi f dx over d, fy is f dy over d, fz is f dz over d. So ingat this is merely derivation. Okay, so you kena tengok balik lah how it is derived. Boleh tak? So kita nak tengok contoh lah kat sini. Kita tengok 2-3 contoh kat sini. Oh, satu contoh saja. Nanti kita tengok lagi satu contoh lah after that. Boleh?
Boleh Doktor.
Semua dah senyap tu. So kita tengok sini. Maybe kadang-kadang kita tak nampak. Bila tengok soalan insyaAllah boleh tengok. Okay. The tension in the guide wire is 2,500 Newton. Right. So guide wire tu ada tension of AB tu sebanyak 2,500 Newton. Okay. Determine the component Fx, Fy, Fz of the force acting on the ball at A. Okay. Dia nak suruh kita cari this Fx, Fy, Fz of this force AB ni. Single force AB ni, FAB ni kita kena resolve it into its Fx, Fy, Fz. Okay. The angles theta x, theta y, theta z defining the direction of the force. Okay. Right. So the guided solution is based on the relative location of the points A and B, determine the unit vector pointing from A towards B. Right. Acting on the ball at A. Oh, so dia coming up from A lah. So dia FAB lah. Right. Apply the unit vector to determine the components of the force acting on A. So ni yang kita nak resolve it into its components tu. Kita kena buat dia dalam sebutan unit vector. Okay. Noting that the components of the unit vector are the direction cosines for the vector. Okay, so direction cosines tadi adalah lambda tadi. So noting that the components of the unit vector are the direction cosines for the vector, calculate the corresponding angle. So dia nak kita cari cos theta x, theta y, theta z, because dia kata components of the unit vector are the direction cosines of this force vector. Okay, dia nak kita cari ni theta x, theta y, theta z. Okay, based on our answer nanti. Right, kita akan dapat yang ni kan nanti. Kita dah resolve dia, kita akan dapat ni. So kita can find this easily lah nanti. Right. So first off, as you can see here, okay, kat sini kita tengok dulu location of A ni. Di manakah titik A terletak? So A is terletak okay, kat mana?
Paksi X.
Tak, dia not really on passing X. Sebab awak tengok ni dia ada 30 meter ke belakang. Betul-betul kan gambar macam ni macam confusing sikit, tapi sebenarnya dia di atas daripada paksi origin ni dia terletak 40 meter ke sini. Right. Oh, silap. Alright, sorry. Acting on the ball at A. Okay, so FAB. So ini would become FAB. So anak panah dia from apa saya cakap, tip to from tail to the tip, right, ataupun head, right, daripada tail to the head. So direction of FAB ialah ke arah sini. So this would become the origin. Okay, now it is located negative 40 X ataupun I 30
Macam mana nak tahu dia punya echo tu kat mana tadi?
info apa
Ya tu yang AB tu, macam mana echo dengan kepala dia tu?
Oh, okay. So dia cuba baca kat sini, kita tengok balik kat sini. Soalan dia tadi, the tension in the guide wire is 2500 Newton. Okay. Components Fx, Fy, Fz of the force acting on the ball at A. Okay, so ini would be the point of interest, our point of interest, right? Our point of interest. Okay, so point of interest. So that force would be going out from A. This is our point of interest, so meaning the force would be going out from A lah. Kita regard dia semua going out from A lah. Ini assumption kita, right? So kalau kita dapat jawapan dia negatif, so sebenarnya dia terbalik lah. Dia macam tu lah, right? So kita assume that this force is going out from A. So FAB, okay, daripada tail to the head, okay, direction dia. So dia ke arah sana lah. Boleh tak?
Boleh betul.
Okay, so direction dia kat sini, ke arah ke atas ni. So vector AB okay, so kita tengok lokasi B ni. Okay, vector AB ni dia ke arah B ni kan. So kita tengok dia punya location lah. So kita tengok location of A would become X1, Y1, Z1. So A is apa tu? 40. Di dalam paksi X dia 40. Paksi Y dia kosong. Okay, sebab dia panel to the Y axis. And then untuk Z dia ke belakang. So kalau Z the direction that going towards us is positive. Okay. So maksudnya kat sini dia punya untuk dia punya Z is negative 30. Right? So kat sini. Saya betul tak boleh tulis? Tulis ke? Dekat. Okay. Untuk A. Okay. X1. Y1. Z1. Right. B, X2, Y2, Z. Okay, so from A, so from A to B, AB would be, so AB, the vector AB would become X2 minus X1. Okay, Y2 minus Y1, Z2 minus Z1. Right, so it will become negative 40, right, Y2 minus Y1 is 80. So ini kalau di dalam sebutan koordinat dia lah. And then this is 30. Right. Okay, so this is basically negative, this is 40, 40, kosong, dengan negatif 30. Okay. Sama dengan X2 is kosong, kosong, my Y dia adalah 80. 80. Okay, jadi dengan kosong. Ada dekat situ. Right, so this is basically dia punya. Nampak tak? Lokasi untuk point A dan juga lokasi untuk point B. So the vector AB ni, so ini sebenarnya bold lah vector, force vector AB ni. Saya tak boleh nak boldkan dia. Ni saya besarkan dia je. Okay, tak boleh. Sama je. Right. So this force, so the displacement of this A from A to B ni berlaku. So it will be equal to negative 40, 80 and 30. Right. So untuk penempatan koordinat ni okey ke? Faham ke? A dengan B ni? Ada yang
Faham
keliru
doktor?
ke? Boleh
Boleh.
Alright. So how much that this force vector has displaced ni bersamaan dengan A, B. Okay. Ni force vector lah. Force vector AB ataupun displacement AB ni is equal to negative 40 mi. Okay. Because I is showing the direction lah. 80 m J plus 30 mk. Okay, direction of this one. Okay. So AB. Okay. Okay, dia punya this force vector AB ni, dia punya magnitude is negative 40 squared plus 80 squared plus 30 squared is equal to 94.3 m. Alright, so just now we have said that lambda ni adalah sebenarnya unit vector of this force vector F. Alright, so yang ini tadi, kalau you ingat lagi, nampak dia 1 over D, the scalar, times dengan this one. Okay, dengan dia punya vector force component. Okay, 1 over 94.3 darab dengan this force vector component of AB. Okay, and then kita asingkan dia jadi negatif 40 bagi 93.1, 80 bagi 93.1, 30 bagi 94.3, dia akan jadi beginilah. This is the lambda ataupun direction cosines of this unit vector of this vector AB. Okay. So lagi satu kita dah tahu kat sini. Okay, F force vector is equal to F scalar darab dengan unit vector ataupun direction cosine lah. Right, lambda ni is actually unit vector lah. Alright, unit vector. Tapi dia terletak di atas our single force vector tu. Kalau unit vector, dia terletak di atas paksi ni. This is unit vector, right? Kalau lambda, dia terletak di atas unit single force vector tu. Nampak tak beza dia? So this is what kita, sebab tu dia dikatakan direction cosine. So it is actually located on the force vector. Kalau unit vector, dia terletak di atas vector komponen. Di atas paksi X, Y, Z. Nampak tak beza dia?
Tak nampak.
Okay. Sekejap saya tengok sini. Sekejap mana ni. Kalau kita tengok balik. Where is unit vector? Unit vector is. Okay. Unit vector. This is our unit vector kan. Okay. Dia parallel to the X and Y axis. Okay. Dia terletak di atas paksi. Okay. Kalau lambda tu, direction cosine tu, yang lambda tu dia terletak di atas this force vector, single force vector. Kalau unit vector, dia terletak di atas the vector components. Yang kita dah resolve, sebelum kita resolve, lambda tu dia ada atas unit vector, lambda terletak di atas single force vector tu. Kalau unit vector, dia terletak di atas vector component. So sebab saya dah cakap dengan awak, satu vector kita boleh resolve dia kepada beberapa dua atau tiga vector components. Right? Depends lah sama ada 2D atau 3D. Okay, unit vector dia terletak di atas vector components lah. So yang nampak kat sini. Dia terletak di atas this one. Lambda terletak di atas sini. Ataupun resultant of this one lah. Of the force component ni resultant ni kan. Lambda kat sini. So direction cosine lah, sebab tu dia dipanggil direction cosine. So ia merangkumi ketiga-tiga direction ataupun dia merangkumi resultant force punya direction. Okay, saya harap awak boleh kecap kat situ lah. Boleh tak?
Boleh.
So ingat lambda di atas force vector. Okay, kalau kita resolve force vector into its component, dia akan mewujudkan unit vector. Okay. Maknanya unit vector dia parallel to the axis. X and Y and Z axis. Kalau lambda dia parallel to the force vector. Sebab tu dia merangkumi ketiga-tiga direction. Right. So tak apa tu nanti you could, but this one is the basic for dynamics later on. So you kena tahu lah ya beza dia. Unit vector located parallel to the axis after we have resolved this force vector into its component. Tapi lambda is actually carrying the direction of the this vector force ataupun the resultant, okay, of this vector component. Sebab satu force vector kita boleh resolve dia kepada dua atau tiga vector component. So component sudah kecil. Okay, dia macam pecahan anak kepada resultant. Macam itulah. Right? Okay. So beza dia lah lambda and also unit vector. Unit vector dia selari atas ni. Tapi untuk lambda dia akan selari di atas force vector yang kita belum leraikan. Okay. Okay. So this is the equation just now. Vector force is equal to F times dengan lambda. So this is 2,500 Newton, right, times dengan this lambda. Right, so you dapat jawapan ni lah. So this is the components of the force. Okay. So ini adalah components untuk AB, force AB. Boleh?
Boleh doktor.
Okay. Kalau untuk sudut dia pula, so noting that the components of the unit vector are the direction constant for the vector. Right. Okay, kat sini. So this ada lambda kat sini. Calculate the corresponding angle. Right, so here comes from this one lah. Right, so kita dapatkan angle dia. Sebab this cos, maknanya negatif 0.424 is equal to cos theta. 0.848 is equal to cos theta y. 0.318 is equal to cos theta z. Right, so kita dapatlah 119.1, 32 and also 71.5. Right, kita equate these two. Okay, accordingly, ataupun respectively lah. Right.
Doktor, boleh ulang yang part angle?
Angle, okay. So lambda is equal to cos theta x times I, direction I, cos theta y, j and cos theta z, k. Right, so ini adalah bersamaan dengan this one. Yes. Okay. Tak boleh lah. Okay ni. Dia bersamaan dengan yang ni apa tu. Okay, yang ini. Okay, lambda is equal to the value of displacement over dengan dia punya scalar of displacement. Alright. Okay, so kita equate this one to the direction cosine punya rumus. Okay, lambda is equal to cos theta x I plus cos theta y j plus cos theta y z. So that one comes from here. Itu adalah yang derivation yang kita dah buat earlier. This one. Nampak ni? Right. This one. You replace there. Okay, so then after that you boleh equate lah. Cos theta x is equal to negative 0.24. Cos theta y is equal to 0.848. Cos theta z is equal to 0.318. So dia dapatlah theta x is equal to 115.1. Okay. Theta y 32, theta z 71.5. Can you keep up?
Okay, dapat doktor. Ya doktor, okay.
Okay. So that's the end for chapter 2. Okay, so kita dah dekat pukul 4 Okay. Susah tau sebab saya tak ada pen. Tak ada pen nak tulis. Sekejap saya stop sharing dulu. Stop presenting. Sekejap. Yang lain-lain diam je. Boleh ke? Tak boleh beritahu.
Boleh doktor, boleh.
Boleh doktor.
Tak, mula-mula memang macam tu tapi kalau boleh daripada awal awak dah boleh tackle awak punya kelemahan tu, so senang lah. Okay, jangan diam je. Tu nanti sampai hujung susah. Nanti susah lah sebab nanti dynamic dia akan jumpa lagi and dia lebih lagi in depth lah. Cumanya dynamic dia benda tu moving lah, moving particle, moving rigid bodies. Static dah senang. Bukanlah senang, I mean compared to dynamic lah. Tapi kalau you boleh faham dia punya principle, insyaAllah boleh buat dua-dua. Kejap Let's see if I have the solution for that one. Susah contoh-conteng. Korang selalu buka makan apa? Beli? Ke diorang bagi? Korang kat college kan?
Masak doktor.
Masak? Kat college?
Rumah sewa.
Oh, rumah sewa. Pak Wan dah duduk rumah sewa
Saya repeaters.
Oh, okay. Sekarang tak ada dah kan macam yang ada kafe tu yang bagi makanan tu dah tak ada kan? Zaman saya dulu ada.
Tak ada doktor. Sekarang
Tak
beli
ada.
sendiri.
Dulu ada macam kafe, bukan kafe dia panggil kantin benda nama dia. Okay. So basically yang untuk soalan lama saya dah stop share pula. Sekejap. The entire screen. No, window a tab. Share a window. Tutup dulu. Sekejap. Okay. Okay, so basically yang ni pun samalah sebenarnya. A frame ABC is supported in part by cable DBE that passes through a frictionless ring at B. Okay, frictionless ring at B. Knowing that the tension in the cable is 380 Newton, in the cable is 385 Newton. Right. Determine the components of the force exerted by the cable on the support at D. Alright, so kalau you tengok kat sini, inilah saya nak tunjukkan dia punya solution lah. Right, so you boleh tengok. Okay, so basically samalah jalan kerja dia macam yang tadi, yang dalam soalan yang tadi. So you boleh cuba buat Okay, saya tunjuk sikit je. Okay, so sama je. So you boleh cuba buat lah. So you cari DB and also BE. Right. Sama je, you follow through this method. This equation. This question punya solution. Right, so nanti kalau nak jawapan boleh bertanya ataupun you mesti benda ni dah recorded kan. So you can look at the video nantilah yang tadi tu ataupun ada yang sempat screenshot. Okay. So try buat lah yang ni. So you lebih faham. Right. So sama je lah. Benda you cari untuk DB and also EB. Because it is mempunyai point yang sepunya B ni. Right. So you boleh guna. So boleh try. So if you have any question you can ask. Saya akan beri link to Google Form, right? Sekejap. Okay. Doktor bila boleh kelas face to face? Oh, Muhammad Uzair. Sepatutnya boleh dah. Tapi sebab saya tak ada kat office FKM. Sebab saya kat office lagi satu. Office apa? Office bangunan wawasan. Sorry tau. Nanti insyaAllah kalau next week Khamis saya boleh datang ke office PKM saya kita buat kelas face to face. Boleh je buat kelas face to face, tak masalah. Sebab actually saya dah pernah pergi tengok kelas tu. So around 40 something tables and chairs, so you can fit in dalam satu kelas lah. Kalau ikutkan hybrid ni, separuh kena kat online, separuh dalam kelas. Kalau untuk hybrid punya kelas lah. Macam kita kan, kita kena buat dua sesi. Okay, minggu ni part A dekat rumah, dekat online, part B face to face. So sometimes tapi lately ni belum ada yang berjaya buat hybrid lah, sebab kelas yang saya nak guna tu dia ada masalah something, kabel ke apa. So ramai yang buat face to face terus ataupun terus online. Sebab kalau tak, kita kena buat separuh-separuh. Maksudnya half of you would be in group A online, separuh lagi kat kelas. Kalau nak buat, boleh next week kita buat face to face terus. I mean 30 lebih tu masuk dalam satu kelas. Tapi kena pakai mask lah. Right? Boleh?
Boleh Doktor.
Boleh.
Okay, so next week lah insyaAllah boleh lah. Next week pun chapter 3. Chapter 3 macam susah sikit. Not really susah lah. Dia macam extension of the statics of particle. Dia jadi rigid bodies. Itu je lah. Sila isi Google Form tu. And then nanti check dekat Google Classroom. Okay. I'm posting up two questions lah for you to so that you can do during you punya masa senggang hari Selasa tu kan, cuti kan. Okay, nanti kena submit through Google Classroom as well. So siapa yang belum join Google Classroom, boleh join So is there any question for me? Any question? Kalau tak, we may end the class with tasbih, kifarah and suratul as. Okay. Okay, so far so good. So far so good je Uzai. Right. Alright, so kita end the class with tasbih, kifarah and suratul as. Assalamualaikum. Thank you.
Waalaikumsalam. Thank you Doktor.
Alright, welcome.
Thank you, madam.